Can you see my screen?
Yes, sir.
Okay. So we are talking about cellular automata as technology. Let us briefly look what we have said in last class. So cellular automata, cellular automaton is a mathematical tool. I mean, which is also defined as a discrete dynamical system. Okay, but accelerometer can also be considered as technology. Okay, so by technology we mean a collection of techniques or methods or processes, right, used to provide some services or solution to some problems or accomplishment of an objective such as scientific investigation, right? So there's a technology. Actually, it is a collection of techniques. We show that cellulometer itself, okay, it acts as cellulometer acts as a technique to solve some real life problems. For problems, we have given some examples, so, such as cellulometer can be used to generate pseudo-random numbers. Cellulometer can be exploited to design VLSI test circuitry. Then it can be used for crypto system design. It can be used for pattern classification recognition, image processing. Sometimes it used in sensor network. It is used in artificial life. I mean, to modeling of artificial life. So the matter they are used. So there are some, these are the some, application areas where cell automata have been successfully used. Right. Apart from that, there are many. There are many actually. If you search, you'll find many applications where cell automata have been successfully used. However, they're the most frequently used things, PRNG, Cellular number generation or Cellular pattern generation, etc. It's a very widely used application area. Similarly, in 90s, VLSI circuit design and test, in this domain, Cellular have been explored in a that way. So first one is pseudo-random number generator. So pseudo-random number generator means, a generator that generates pseudonym patterns, pseudonym numbers. Pseudonym numbers are some numbers which are not random, but appear to users that it is as random. Okay, so pseudonym numbers are generated by means of some algorithm, right? Some deterministic algorithm. So since it's the algorithm, so the algorithm cannot generate the random numbers, because from one number, what is the meaning of random numbers? Random numbers are those numbers where two numbers are not correlated. Okay, you can find any correlation. So random from one number, you can say which number is to be produced next time. Okay, but since you are generating the numbers by means of deterministic algorithm, so from one number you can, from the previous numbers you can predict always what is the number, what is the next number. So any algorithm cannot generate random numbers, but it can generate some numbers which are appearing to us, to the users, as random numbers. So we call it pseudo-random numbers, right? So cellular automata can be used to generate such pseudo-random numbers. So these are the few properties of pseudo-random numbers: as uniformity, independence, large period, reproducibility, consistency, portability, efficiency. So any algorithm which generates pseudo-random numbers, so they have to follow these properties. The number generated by the generator, they have to be uniformly distributed. The numbers generated by the generator, they have to be independent from each other. When one number is independent from others, so etc etc. So large period. So since the system is finite, so a number will be repeated after some time, but that period of the repetition should be as large as possible. Okay, so these are few properties which you have discussed. So these properties are to be satisfied by any PRNG. Oscillometer generates the numbers. How? So we want to, if we treat the numbers, if we treat the configuration as numbers, and oscillometer generate configurations one after another, so we can say that oscillometer can generate the numbers, right? So in other words, so oscillometer generates configurations. So if we apply some function, okay, some mapping which maps the configuration to some number, then we can say that the automata can also generate the numbers, right? So yet the point is the point is that automata are generating numbers. So if those numbers appear to us random, then we can claim that automata can generate pseudo-random numbers. First, ECA30 Rule 30, Wolfram's Rule 30, that was used to generate pseudo-random numbers. It's a Wolfram proposal in 1984 or in early 80s. So this is a space-time diagram. Space-time diagram. So several techniques are used to extract numbers from this space-time diagram, right? So Wolfram also showed that that the numbers, the bit sequence generated by the middle one, middle cell of this diagram, okay, that sequence does not repeat even after 1 billion steps. In fact, he posed a challenge that whether ECA30 generate the sequence, the middle bit of this pattern, the generate sequence, whether the sequence is aperiodic or periodic. That we don't know. There is no proof, but it appears to us that the uh, uh, the sequence is aperiodic. So ECA30 was first used to generate pseudo-random numbers or patterns. Sometimes we call it pattern. See, here is 0, 1, 2, etc. Sorry, 0, 1, 0, 1, 1, 1, etc. Sequence is there. So it's a pattern of 0 and 1. Okay. If we convert the patterns to number, we can call it pseudo-random numbers. Or if we don't convert it, if we just concentrate on the configurations, we call them the patterns. So sometimes we call it pseudo-random pattern generation, right? Anyway, Rule 30 was first proposed to generate the numbers, pseudo-random numbers or pseudo-random patterns, but the point is there's an issue. What the issue? Issue is ECA30 is an infinite CA. It is divided over infinite array. Now, if you want to implement really, then infinite consideration of infinite size is not very practical. You can't infinite CA you can't implement infinite CA in any computer, and and so the proposal is not very useful if you want to use cellular automata as technology. How Wolfram did so? So he has taken enough array, enough lattice size, okay, and then he used to generate the numbers, right? And he calculated, calculating somehow that the size and the numbers are generated by the CA, they will have that effect, and the size will not make the patterns as patterns of finite CA, right? So there is the style of Wolfram to use ECA30. Anyway, the point is infinite consideration of infinite CA is not very good if you want to if you want to uh, uh, if you want to uh, use cellular automata as technology. So our obvious choice is finite CA, right? So for pseudo-random number generation by finite CA, we have we need non-uniform cellular automata. There's a special type of non-uniform cellular automata that is called maximal length cellular automata. This cellular automata, the special type, if you have n number of cells, right, and if you have n number of cells, and say for example two number of states are there, so then how many? What is the size of configuration? 2 to the power n, right? Now, maximal and Cs are those Cs which include almost all configurations in a single cycle. Why I'm saying almost all? Because it always excludes one. For example, if you have linear CA, the trivial or zero configuration is excluded. So all non-zero configurations of a linear CA, linear maximal and CA, are covered by a single cycle. So this kind of automata, they are very effective. Why? Because as we are saying that to be a good pseudo number generator, the cycle length should be high, very high. And here, cycle length is highest, it's to the power n minus 1. Okay. So this kind of automata, they are very useful. So you can see the example I have given here. So if you take 9150, 9150 is a under null boundary condition, it's a Maxwell and CA. And you can see the state transition, the transition diagram. If you start from any configuration except all zero is trivial one, you have to exclude it always. So if you start from any non-trivial configuration, you will see that the rest configurations I mean, you can see that they will appear one by one. Okay, so it may appear to you that from one configuration you are getting another configuration, it's a new configuration. From that another new configuration, as if you have all non-zero configurations in one basket. You are choosing the configurations. I mean, one by one, and as if there's some kind of randomness. Because from one configuration, if you don't know the CA, then you can predict which is your next configuration. So it looks like random. So therefore, in throughout the 90s, the Maxwell and CAs, in particular, maximal length, non-uniform ECS, right? They have been used to design pseudo-random pattern generator, or you can call pseudo-random number generator. So in this way, the maximal and pseudo-meter, they are used as pseudo-random number generator. So I was talking that number generation and pattern generation, they are not same. I have said that, mathematically they are different. Patterns and numbers, they are not same. But as I said that when a configuration is given, configuration is a pattern. Configuration can be treated as patterns. Okay, so automata generate configurations. That is, automata generate patterns one after another. So I need a mapping and function, okay, which translate the configurations to some numbers, right? So although pseudonym numbers and pseudonym patterns, they are not same, but in my cases, in my discussion, sometimes I'll use the terms interchangeably. Okay. Anyway, so this Maxwell and automata can be used as PRPG, pseudonym pattern generator, or pseudonym number generator. So we have talked about a theorem that a linear CA is maximal and CA if and only if its characteristic polynomial is primitive. So one CA is given, one CA is given, the CA is linear CA. And there's theorem, I shall not prove the theorem. I have not proved in the last class also, that I'm just giving the statement that a CA is maximal and CA if and only if its characteristic polynomial is primitive. This is for a linear CA. Okay, and there are other theorems, like if you want to talk with, if you want to consider the complemented CA. So then if the linear part is maximal and CA, then is any of its complement CA. they are always maximal in CA, right? So from the single linear maximal in CA, we can get many complemented maximal length CA. However, there is no method till now to generate non-linear maximal length CA. In literature, most of the works on maximal length CA, they consider linear maximal length CA. Okay, so many theories are there. So I'm not going to cover them. Just I'm telling that if you want to use maximal and automata, be it linear, be it complemented, so what you need a tree matrix for the CA, and if that matrix, if the characteristics polynomial of that matrix is primitive, then the corresponding cellular is automaton is maximal length cellular automaton. So this is the sum in summary. Maximal and cellular can efficiently be used to generate pseudo-random numbers or pseudo-random patterns. So these things I have said that I have also said that why these kind of CA they are very popular. They have become so popular. The first reason is they can easily be implemented in hardware. So hardware implementation of the CA is one reason of its popularity. So if you know that okay, this kind of CA can generate random numbers, you can easily implement them by hardware. Note that traditional techniques of generating random numbers, for example, LCG, which you used in say in your programs, so C programs, RAND. So for LCG, it is not so easy to implement them in hardware. So that is one reason why CA becomes so popular as pseudo-random number generator. So, especially at the time of VLSS circuit and at the time of for the VLSS circuit test solution, it has become very popular. For VLSI circuit test, right? What is our requirement? Our requirement is we want to generate, we want to design some circuit whose, you know, his area overhead is very less, whose overall cost of designing the circuit is very less, and especially for the design of BIST structure. BIST is built-in self-test structure. Cellular automata become very popular. So up to this part, we have discussed in last class, and we have said that pseudo-random pattern generator (PRPG) can act as test pattern generator. Now let us briefly discuss what is built-in self-test. So built-in self-test, you understand its name, built-in self-test. It has a capability of a circuit to test itself. Okay, so you are developing some some circuitry, electronic circuitry. So while they design some circuitry, we always have to test the circuit whether it's functioning properly or not, right? That is essential. In fact, be it hardware, be it software, testing is always needed, right? So what we do, what is the popular technique nowadays? You do something so that the circuit can test itself automatically. Its name is built-in self-test, BIST. So what is that? The point is here that a small circuitry is placed inside the main circuit, right? So that small circuit is also manufactured during the manufacturing of the whole chip. Now, when his manufacture is complete, then if you put power, then that small circuit becomes active, and that small circuit can test the circuit automatically. So its name is built-in self-test. So therefore, so that whole circuitry, it has some function it has to perform. Additionally, it has a small unit which can test itself. Okay, so it has a capability. So it's a circuit of a circuit to test itself. We call it built-in self-test. Now this built-in self-test, you know, it has to be very small. No? It should not. Its overhead should not be very high, right? Because it has no additional functionality. Some circuit, some electronic circuit, it performs some task, but that small circuit which is used to test, that does not help in performing that task. What it does, it just tests whether it's correct or not. So therefore that small, that small circuit, I mean that part, the testing part, should be very small. That is the primary requirement. So beast should be as small as possible. Its overhead should be very, very less. Overhead means, it's, so one is area overhead. At the age of VLSI, so area is most important thing, right? So in your chip, so how much area it is taking, that's very important one. So area overhead of the circuit should be small. Anyway, so in that base, there are two main components. One is called test pattern generator, TPG, and output response analyzer. In my slide, you can see is I have given a basic architecture of BIST. First is TPG, test pattern generator. It generates some test patterns. What are the test patterns? So 1, 0, 1, etc. test patterns, right? These patterns, test patterns, are fed into the circuit. We call it CART, circuit under test. Okay. So when it passes some pattern, 0, 1, 1, 0, there are many gates, many logic circuits, etc. So they'll have some output, right? Now, that output may be correct, may be incorrect. If your circuit is all right, if your circuit has been manufactured properly, then your output will be proper. Will be correct. And if there is some defect during manufacturing, then your output will be wrong. So therefore, whether the output is correct or not, that is to be analyzed. That is analyzed by the other unit called ORA, output response analyzer. Okay, so in one end it generates the patterns, it goes to the circuit, right? So these patterns are the input, right? So then it gets its response. The circuit response means it gives some output that is analyzed by ORA. Now, if it's found that okay, there are some severe problem, then the circuit is rejected. Otherwise, it's okay. Interestingly, you understand that once it's manufactured, TPG or ORA, BEAST, this circuitry, they are permanent. Okay, when you purchase any electronic circuit, be it your mobile phone, be it your be it your smartphone, be it anything actually, so you can always find a small circuitry there inside of your system, and they are always testing your pattern. They're useless, but still they keep on testing your circuit. Okay, so there is one issue. Anyway, if once you approve that it's okay, circuit is okay, then if people generate the patterns and if they analyze, there's no problem. So this is the basic architecture of BIST. So TPG, it generates the patterns, the input to the circuit, and then it gets some output, which is analyzed by ORA. And so here, the both the components, TPG as ORA, both are important. So cellular automata, they are used actually to generate test patterns. Okay, so cellulometer, they are used as test pattern generators, but not ORA. ORA, there are some different circuitry. We shall not discuss about ORA. So since we are discussing cellulometer, so we shall discuss that cellulometer can generate several kinds of test patterns. Now, test patterns is okay, but there are several types of test patterns, right? Because you have to test the circuit, so you have to pass, pass some record patterns to the circuit. So there are several types of test patterns. Let me tell you that test patterns one by one. See, one is deterministic test pattern. Okay, so deterministic means a circuit is given to you, and you know that to test the circuit, you need to supply these set of test patterns. Okay, these are called deterministic, and it is obviously it is specific to cart. Cart means circuit under development, circuit under test. Okay, so deterministic test means, say a circuit is given, you know. So as designer, you want to test the circuit with this set of patterns. Now, since the set is fixed, we call it deterministic. Okay, so deterministic is called deterministic test pattern, specific to cart developed via ATPG. AT means automatic test pattern generator. So we call it TPG, test pattern generator. Sometimes we put A, automatic test pattern generator, because we shall see that our accelerometer is automatic test pattern generator. So I am not feeding the test patterns from outside world. So it's called automatic test pattern generator. Okay, so it's called ATPG. So these are deterministic test patterns. So there is another kind of test patterns called algorithmic. Okay, so used to test regular structure and specific fault models. So test patterns are generated by some algorithm. Okay, so this is not of our, not of our interest, but it's possible. Before that BIST structure, this algorithmic structure was there. Number three is exhaustive test patterns. It is sometimes required, means all possible input test patterns are generated. So if you have n input combinational logic circuit, so then how many test patterns you need? 2 to the power n. Means you want to supply all possible patterns to test whether it is performing okay or not. It's performing well or not. So exhaustive test pattern. For large circuit, for large n, you understand it's very costly actually. And how can you generate the the exhaustive test patterns? The ways you need to counter. You can use a counter, right? Counters, counters can generate all the numbers. Okay, counters are used uh, for the exhaustive patterns. Next is very important, called pseudo exhaustive. So instead of supplying all patterns, I shall supply exhaustive patterns only some part of the some only for some inputs. So exhaustive for some inputs, but not for all inputs. Also, I shall tell you with some example what is the meaning of pseudo exhaustive. Pseudo exhaustive is important. Okay, and then is pseudo random that we have discussed right now. Pseudo random means some random patterns are input to a you know circuit. Okay, and last two is weighted pseudo-random. Weighted pseudo-random is sometimes used that sometimes the weight of one is more than weight of zero, or weight of zero is more than weight of one in a pattern. Some special types of patterns have more weight, right? So they're called weighted pseudo-random patterns for special type of circuits. We need to give some this kind of input. And finally random, so this is not very useful because we can't generate random patterns always. So these are test patterns, right? So what are most important here? One is you can say deterministic pattern, right? Exhaustive pattern, pseudo-exhaustive pattern, right, and pseudo-random pattern. So these types of patterns you may need to test different circuits. So your TPG, test pattern generator sometime should be able to generate this kind of patterns. We claim that cell automata, they are universal pattern generator. Cell automata can generate all kind of patterns which a circuit need to be tested. So, in particular, we classify, the patterns in four ways only. Pseudo-random pattern generator. So, your cell automata can generate pseudo-random patterns. It can generate pseudo-exhaustive patterns. And third one is important. It's called PRPG with prohibited pattern set. This is very interesting property, very interesting, set of patterns that we shall discuss. But it's a new class of patterns, test patterns, so which sometime we may need to test some circuit. And finally, deterministic test pattern generator. So we claim that all the patterns can be generated by cellular automata. So if they can do so, we can claim that cellular automata as universal pattern generator. What you need that can be done by, by a cellular automaton. Okay, so pseudo-random pattern, what is pseudo-random pattern that we have discussed, we understand also. And if you give input, say Maximal and Cellular Automata, that can generate pseudo-random patterns. Okay, that's okay. Now, what is pseudo-exhaustive pattern? So, exhaustive is pseudo. What is that? Say, consider 3-bit circuitry. So, this is the exhaustive pattern. Okay, suppose your pattern generator is generating patterns in this way. Say your circuit is 3-bit circuit, right? 3-bit circuit. So three input. Three inputs are there. Okay. So here you can see in this figure 1 1 1. It starts from 1 1 1. Then it's 1 0 1, 1 0 0 0 1 0 0 0 1, all 0. Okay. So you can see from all 0 to all 1, all the patterns are generated. So these exhaustive patterns. Sometimes, as I've said, you need exhaustive patterns. Okay. But what is okay? One more thing. While I was talking about Cellular Automata as universal pattern generator, I have excluded from here the exhaustive pattern generator. Right? I have said pseudo exhaustive, but not. I have not said exhaustive pattern. Why is so? Because in general, we do not use exhaustive patterns, because exhaustive patterns for large circuit, they are very costly also. And if you really need so, with an approximation, you can use maximal length cellular automata. So where all 0 pattern will not be there. Oh, sorry. All 0 pattern will not be there, but apart from all 0 pattern, all the patterns can be generated by a Maxwell and CA. So since we don't need in general the exhaustive pattern, so I have excluded from here exhaustive pattern from here. Anyway, the figure I have shown here, for 3 input circuits, all the patterns are generated. So these patterns are exhaustive patterns for 3 input circuits. This is pseudo-exhaustive pattern. Why I am saying pseudo-exhaustive pattern? Look carefully. 3 input circuit. So there are only 1, 2, 3, 4. 4 test patterns are there. So this is 4 means this is not exhaustive. it should have 8 patterns. Out of 8, only 4 I have supplied. And now you observe carefully that, so last two bits, observe last two bits here. It is 1 1, then 0 0, then 1 0, then 0 1. So these last two bits have appeared exhaustively in this pattern set, right? In this particular example, first two bits also appeared exhaustively. So 1 1 1 0 0 1 0 0, right? So anyway, so what you see here, although the patterns have not appeared exhaustively, so three input three input patterns, so it should have to the power 8, 3 means 8 patterns, but there are only 4 patterns. But what you see here, few bits, last two bits, they have appeared exhaustively. So these kind of patterns are called pseudo exhaustive patterns. So first last two bits, they appear and they have appeared exhaustively, right? These kind of patterns sometimes we need. So in a circuit, say if we understand, if we think that okay, say n bit circuit, say I and j bit, or say I, j, k, l, etc. These 4 bits, they have to be tested exhaustively. Some circuitry is there, okay, which are very important, which have to be tested exhaustively, but not the whole circuit. You don't want to test the whole circuit exhaustively. For that case, arbitrary patterns, arbitrary testing may be okay for you. But you have to test some part of the circuitry exhaustively. For that, you need pseudo exhaustive test patterns. Okay. Theories are there. I shall not go to the theory only. I'm just giving you overview today. That cellular automata, especially reversible cellular automata, okay, reversible linear cellular automata, I'm talking about linear cellular automata, they can generate these patterns exhaustively. So if you can design such cellular automata, non-uniform cellular automata, which are reversible, and in which some patterns, some bits appear exhaustively, then you can use that cellular automata to generate these patterns. Okay, so that much I am saying here, that cellular can be used as, the cellular are having this kind of property where some bits appear exhaustively in in its configuration space. So that kind of cellular can be used to generate pseudo exhaustive test patterns. Now, next, I am saying a different way. See, TPG, test pattern generator without PPS. Just now I have said what is PPS, prohibited pattern set. This is interesting, so I shall give you a brief idea about this one. This is very interesting. See, what we are doing for testing of a circuit, we are supplying some patterns, test patterns. Patterns are testing some part of the circuit, and then it is giving. You're applying some test patterns, then it's testing and it is giving some output. Sometimes it may so happen that some patterns, they are prohibited to the circuit. Why prohibited? Means if you give input these patterns, that may put the circuit in some undesirable condition. What is the pattern actually? Pattern means, you are supplying 0 1 0 1. In the physical level, what you do? 1 means, say you are supplying 5 volt. 0 means 0 volt. Some power you supply, na? Some voltage you supply. That's the meaning of only 0 and 1. In digital circuit, what is the meaning of 1? How we physically represent 1? What is the physical interpretation of 1 or 0? So the threshold value of voltage, say, I'm saying roughly, if there is no power, say if it is 0 voltage, is 0. If it is 5 voltage, if you give input, it's 1. So if you give input like 1 1 0 1, it means you're supplying 5 volt, then 5 volt, then 0, then 1, 0 volt and 5 volt. So you're supplying some power, right? And they're performing some action. Now, in some cases, it may so happen that while you are giving some input, this kind of input, your circuit may be put in some undesirable state. So what you should do? You should not give input those patterns, because you know in advance. Because you know in advance that these patterns may put your circuit in undesirable condition. So while you test your circuit, then you should not give those patterns as input, right? Now, if you give pseudo-random patterns as input to test your circuit, pseudo-random patterns is very popular. Okay, so, and it's a random pattern. It is not deterministic pattern. It's random pattern. So any pattern may come here. Now, during that testing, if some PPS prohibited pattern, some pattern from PPS comes, your system may malfunction. Okay, so in the diagram, I have given this one, that say cycle, you can see that the diagram. So suppose P1, P2, P3, P4, they are the configurations, the patterns supplied by PRNG, TPG. P1 is okay, it's okay. P2 is okay, but when it comes P4, then circuit may burst. Okay, so it's prohibited pattern. So therefore, while the testing, P4 should not come. Additionally, this is the random patterns, it's not deterministic pattern. So P5, P6, P1, P2, they should appear as random patterns. This is the requirement. So the requirement is contradictory. You are not supplying deterministic pattern, you are supplying random patterns. But a constraint is put here, that is some pattern should not come here, right? So we claim that this kind of problem can efficiently be solved by cellular automata. So I shall tell you how can we do so. I shall tell you with some example. This is very interesting, so I shall give you some detail. We shall use reversible cellular automata. Suppose, so take a cellular automata. Suppose these are in the left hand side. You can see some patterns. Suppose this is by PPS, prohibited pattern set. Some patterns are given, 2 4 8, some patterns. So 10 patterns are given here. Now, see, to solve this problem, you understand that you cannot use Maxwell and Cellular automata, because in case of Maximal and Cellular automata, all the patterns will come. So Maximal and Cellular automata cannot help you here. I have claimed before that to test a circuit, Maximal and Cellular Automata can work fine because it generates pseudo-random patterns. But here I'm claiming that maximal length Cellular Automata is not a good candidate. Even it generates good pseudo-random patterns. We need reversible CA, but what is the target? Our target is, these patterns, the prohibited patterns, they are to be placed in different cycles. See, you can see, let me give you solve this problem with some example. Explain this problem with some example. So right hand side of the slide, you can see a CA, right? C is reversible CA. Suppose I have drawn some cycles. Suppose there are 4 cycles. First cycle is cycle of length 1, single pattern, all 0. Then a length of 7, right? Third cycle is length of 15, and fourth cycle is length of 105. Okay. So what is the target? We shall try to accommodate the PPS in the smaller cycles. And the larger cycles will be exploited to generate pseudo-random patterns. Since the largest cycle, it has many patterns to generate. It can generate many patterns. So it can generated patterns may look like some pseudo-random patterns, right? Although its length is not as large as the Maximal and CA, but still it's larger. So it can fulfill our purpose. But important thing is here, the rest patterns, the prohibited pattern sets, the prohibited patterns, they are in different cycles, right? However, sometimes you may not guarantee that all the patterns they will be in the smaller cycles. 1 or 2 patterns may fall again in the bigger cycle. So in the example I have given, what I have shown, that you can see that many patterns they are in cycle length 3, so cycle number 2, cycle number 2 of length 7. So 3 patterns are there. And in cycle number 15, cycle number 3 of length 15, there are 1, 2, 3, 4, 5 patterns are there. What I want to generate the patterns from cycle 4, which has length length 105. In some cases, in very general cases, it may so happen that some patterns they are still in cycle number 4. If there is no pattern, then it's a good one. Suppose consider a good scenario that all the patterns are being accommodated in the smaller cycles. Then what you can do? You can pick up any configuration from the cycle, and you start your CA from that configuration, and you generate the patterns. You know that in the cycle there is no probability pattern, so you can use those patterns to test your circuit. There's no problem. Since the probability patterns are in different cycles, okay, you will never reach to those patterns. This is the property of the cellular automata. Reversible cellular automata, its property. But sometime, if it happens that few patterns, that should be very few patterns are still in the large cycle. Here in the example I have shown the 2 patterns only out of 8 patterns. All are covered by the other cycles, but 2 patterns remains. Two patterns remain here, which are in larger cycle. Right. So here I have written the first and 11th. So just in the figure, all are not here. But so few patterns, say first pattern and 11th pattern. If we start from the 001 0001, then after distance 11, after distance 10, 11th pattern is also a prohibited pattern. Then what you can do? You can set your CA with 12th pattern, right? I mean, so we call it this target cycle, and this is redundant cycle. Okay, so here what I've said here, it is written that apart from this first to 11th, the rest part, okay, if you call it Dmax, distance is Dmax, cycle length minus Dmax, that part remains PPS free. The patterns from this part can be exploited, can be used to test your circuit. Now here, since size is very, length is again very high, very large actually. So the patterns generated by this part will also look, appear to you as uh, random, pseudo-random. So this is a very important property of cellular automata. I mean, this important property of cellular automata can be used to test, used to generate this kind of patterns, pseudo-random patterns without prohibited patterns. Okay, so this is the strength of cellular automata, which can be used uh, to generate test patterns. Okay, so this is the brief about the design PRPG without PPS, prohibited pattern set. So I have not covered here the deterministic test pattern. The similar idea can be used for deterministic test pattern. So in case of deterministic test pattern, you know that you have to supply a set of patterns. A set of patterns you have to supply to test a circuit. Now what you should do? The reverse one. That you find a cell automator, you find a cell automaton, okay, preferably reversible cell automaton, which can generate that set of patterns, right? If it is so, then you start with any pattern, and if you run the CA, the other patterns will be generated, right? So cell automator can generate test pattern automatically. You may ask questions, why we are doing all these things? You may ask this question that if you want to really test this pattern with some, test of circuit with some given pattern, what you can do? You can store all the patterns in some ROM, right? In some ROM, you can put them. That you can always do. All of these patterns you can put in ROM, but that is always costly, right? As I've said at the beginning, that test, overall the circuit should be as minimum as possible, right? So if you want to store all patterns in a ROM, the cost will be very high, right? So we do not prefer, nowadays we don't prefer ROM-based testing. We prefer ATPG, automatic test pattern generator, Cellular or LFSR. They are capable to generate test patterns automatically. Just you put the circuit, and the circuit, the small circuit, Cellular circuit or LFSR circuit, will be able to generate the patterns automatically. Okay. So this is all about test pattern generation by Cellular Automata. So next, move to another application, pattern classification. So what I've said, that is for the VLSI circuit design, filter circuit testing, we can use Cellular can be used as test pattern generator. Here I am showing you that Cellular can also be used to classify the patterns and then recognize the patterns. So for pattern classification and recognition, automata are also used successfully. Uh, so here, unlike the previous case, here we use irreversible CA. In particular, we use multiple attractor automata. You see, in the in the diagrams, transition diagram, so the attractor is there. In this diagram, there are four attractors. What is attractor? Attractor is a configuration, right? Right, which is having length one. Although attractor may have may have length more than one, but here by attractor we are saying single length cycle. Sometimes they are called as single length cycle. Sometimes they are called as point state. Sometimes they are called as fixed point. But the point is, a cycle is formed by a single configuration. Now, if if the cycle exists, cycle is having length of one, then that kind of cellular are called as multiple attractor cellular automata. Now, these kind of multiple attractor cellular automata can be used to classify the patterns. Just for example, I am telling you that you consider the diagram is shown in this figure. There are four distinct tree, four graphs are there: S1, S2, S3, S4. This is a transition diagram of the CA of rule vector 222, 221, 192, 68. Okay, but it is having the four distinct graphs. Now suppose I am saying S1, S2, it is forming class 1, S3, S4, it is forming class 2. Therefore, all the patterns of S1 and S2, what are the patterns here? The configurations of the pattern. So habitant 4, habitant 0, habitant 5, etc. They are the patterns. Okay. These patterns, all these patterns, 4, 0, 2, 3, 1, 5, and 6 and 7, they form a single class. And they're just patterns. 14, 15, 13, 9, 11, 10, 8, 12. They are forming another class. I'm saying that one. Now I say that class 1 is represented by 3 and 7, whereas class 2 is represented by 15 and 11. Why I'm saying so? Because 3 and 7 they're the attractors, 15 and 11 they're also the attractors. So I'm saying so. So therefore, the structure of cellular itself advocates for some classification of patterns. You have to define patterns. Okay, but this structure automatically, you know, classifies the pattern in this way. Okay, so this kind of classification, if you have this kind of structure in cellular automata, then that cellular automata can be used to classify the patterns. Now suppose you want to recognize, so therefore cellular automata can be used as machine here, right? It's a machine. Now how it can recognize a pattern? Suppose, so you have designed the machine. Your machine is the CA with rule vector 222, 221, 192, and 68. Now the machine can recognize the patterns. I claim so. Suppose you are giving input 4, only 4. So you start your CA evolution by configuration 4. Then from 4 you will go to 0, then 0, 2, then 2 to 3. And 3 is the attractor. And if you have this information, right, that 3 is representing class 1, then you can declare that, okay, I have reached to 3, means the class 4 is, the pattern 4 is of class 1, and so on. So therefore, this machine can recognize the patterns, right? Similarly, if you give input as 12, 12 will serial to attractor number 11, attractor 11, which is of class 2, based on my old design. So if 12 is there, then by running the C, I can claim that, okay, 11 is of class, uh, you know, sorry, 12 is of class 2. So therefore, if you have this kind of structure, then you can classify the patterns as a natural classifier, and then after the classification, you can recognize the incoming patterns. So you may see that, okay, there are only four cells, so it's very simple. You can store everything in in your file. But you think that you have 32-bit machine, I mean 32-bit patterns. Then what you need? 2 to the power 32 patterns. So you can store all the patterns, right? What is the importance of machine, right? Why you design the machine? Machine is, I can always classify the patterns, recognize the patterns if I store everything in my database. But in real time, if you want to recognize a pattern, the stagger will not work. Rather, you develop some machine, you learn the machine, it is the learning phase. So during the learning phase, you give some information to the machine that, okay, this attractor, in this case, this attractor means class 1, this attractor means class 2. In real life, how you can do that one? You choose the CA, and you have that basic data set. You train that CA. After training, so you can say, okay, this 3 for class 1, 15 for class 2, and so on. So then after training, you can choose a CA, right? As well as you can designate that this attractor for class 1, this attractor for class 2, etc. Then the machine design is done. Then so learning part is done. Then you test it. This testing part is pattern recognition. So when a new pattern, when a new pattern will come to your system, you have this old information. Based on that, you declare the new pattern, whether it is of class 1 or class 2 or other thing, or of other class. So in this way, that this kind of irreversible CA, we call them multiple attractor. This name is not written here. Its name is multiple attractor cellular automata. This CA can be used to classify the patterns as well as recognize the patterns. It is interesting. It is interesting to note sometime, not always, but sometime, in an attractor. Okay, in the attractor, some bits appear exhaustively. You can see right hand side. You have written, so 4 attractors are there. The attractor are 3 is 1100. I have written in reverse way actually. Uh, I mean 1100. I have written in reverse way. So I can understand. See 1100, 1110, right? 1101 and 1111. Okay, please note that here numbering is in reverse way. Actually, in the other cases, I sometimes use a different way, but here 1100 means 3. First bit is considered as LSB. So here, if you consider that the binary pattern, you can see that last two bits 00, last two bits, they have appeared exhaustively. 4 patterns and 00, 10, 01, 11. This exhaustiveness has additional advantage. What is that? Advantage is here. See, instead of storing 4 patterns, you can store only the exhaustive patterns. You can see the patterns all are unique, na? 001000, the blue one, 00100111. They're unique, right? So why do you store the four bit patterns? Better you store the exhaustive part only. So instead of 3, I can say it 00 only. Instead of 7, I can call it 10. Instead of 15, I can say it 11, etc. So in case of linear CA, okay, in case of linear and complementary CA, sometime in case of even in nonlinear CA, this is the CA is nonlinear CA, you can find this acoustic bits. While we design this kind of machine, we look for the pseudo acoustic bits. Why? Because in that case, I need to store less information about the class. So therefore, in your machine, you design a CA. Suppose you have to design this machine in hardware, right? You have designed the hardware, new pattern is coming, you are giving that pattern as input, right? And the pattern is evolving. So 4, you have given 4 as input, it is restored 3. Then you have to understand 3 is of which class 1 or class 2. Then some information has to be stored either in file or in ROM. Somewhere it is stored, right? Now, what I shall store instead of whole pattern 1100, I shall store only 00. So I shall look at last 2 bits. If it is 00, I shall declare it class 1. See, you can think of a machine, you can think of hardware. A small CA, only 4 bits CA. So its output is captured, 2 bits, captured by a circuit, and it's compared with some stored pattern. Based on that, it gives output whether it is of class 1 or class 2. And that is all. So therefore, this is the design. Therefore, what you can do, you can use this kind of CA as your machine, which can do pattern classification and recognition. So challenge is here, you have to find proper cellular automata. So you have many cellular automata. So all are not having this kind of property. Okay. So I can tell you, I don't have slide, but I can tell you that in case of linear CA, if the characteristic polynomial is like this, x to the power k into 1 plus x to the power n minus k, something like that, then the CA is having this kind of structure. This is the property of linear CA. But apart from this linear CA, in other cases, we don't have such theory. Okay, some theory have been developed. Some theories have been developed. Then arithmetic tree also was used to find this kind of CA. Okay, and they can be also used to arithmetic tree can also be used to find this kind of CA. But okay, so the point is you have to search this kind of CA to design a good machine. So this is about pattern recognition and classification. Just I have just given an overview, nothing else. Apart from this pattern classification and recognition, so another important application is cryptography. So I shall not cover cryptography today, and I shall not cover anymore actually cryptography, as well as they are used in image processing. For image processing also, many authors, many researchers have used automata for image processing. For compression by hardware. Okay, so for the compression we have, for lossless compression, we have that one, the Limbel zip algorithm, LZ77, LZ78. You may know this one. This is algorithms by using which Jeep, zip, or with Jeep they're implemented. And then for lossy compression, there is JPEG. JPEG is the very famous well-known compression. But harder implementation of JPEG as well as Jeep is very difficult. Although nowadays hardware for JPEG is available, but still it is difficult, But Cellular, since its hardware is very simple to implement, so for this kind of compression, hardware-based compression, on-the-fly compression, uh, uh, Cellular was popular one time. Okay, so text compression as well as image compression, Cellular can also be used, but we don't have slide. I don't have slide, and I should have covered it here. Okay, and okay, so there are another technology called N compression, encryption plus compression. So Cellular based encryption is possible. Cellular based compression is also possible. So these two units are merged: compression plus encryption parallelly. It was very useful technique. Called N compression. Using Cellular, they are also used. They can also be used. Recall that in one class I have shown you a programmable CS structure, that is a cellular automata structure which can run any kind of cellular automata. So here what I'm saying, many kind of cellular automata, be it SPARC generator, be it parent classifier, be it compression, etc. But the only property is here we are concentrating on non-uniform ECS only. And if you recall that structure, right, that programmable cellular automata structure, then you understand that these kind of CAs can be implemented by that structure. So once you have that programmable CA structure, and you can implement all these CAs by that programmable structure. So therefore, if you want to use Cellular for different purposes and for different applications, so that structure you can use as universal pattern generator as well as design of other machines. Okay, so I believe apart from these two applications, there are other applications, other areas. Okay, where people not yet tried to use Cellular, you can explore this beautiful structure of Cellular to solve those problems. So I want to mean that in other application areas, what I've said, apart from that, there are other application areas, and there also you can use Cellular uh, uh, for that purpose, for application purpose, because Cellular generate patterns. Okay, these patterns can be treated in different ways, sometimes as numbers, sometimes as patterns, etc., etc. Okay, so this is all. So by this, I want to conclude this course here.